This webcast continues in Worksheet 6F, where we're dealing with quantitative energy conservation problems. Let's look at number 8. Here we have a cart that is moving at 5 meters per second when it collides with a spring. And at the instant that the cart is motionless, what is the largest amount that the spring could be compressed? Okay, and there's no friction in this situation. So I'm just going to do a little sketch for myself. So I've got a cart that's moving, and it runs into a spring and is going to cause the spring to compress. Okay, and apparently at position A, the cart is moving, and the spring, I'm assuming at that point, is, it's just fine. It's not compressed yet. It's at equilibrium. So at the beginning, the only energy in this system that includes the cart, the spring, and the earth is going to be the kinetic energy of the cart. But at position B, the cart is motionless because it has compressed the spring. It's probably getting ready to change directions, but I'm looking at it at that instant when it's motionless. So there's no more kinetic energy. The spring is compressed. And let's see, there is no friction, so I won't have any dissipation. And so I think all of that energy that originally was kinetic has now been redistributed in this system to be the elastic potential energy stored in the spring. If I wrote my conservation equation, it would say that the change in the kinetic energy equals the change in the elastic potential energy. Okay. Now, so far this is very similar to things we've done before when we've used energy conservation diagrams. But now I actually want to calculate and find the compression of the spring. Okay, I'm going to start with that energy conservation equation, and in place of each term, I'm going to put the formula to calculate that amount of energy. The kinetic energy of the cart at position A, I would get by finding half of the mass of the cart multiplied by the square of the velocity. And the elastic potential energy in the spring at position B would be half the spring constant times the displacement of the spring squared. So see, I have substituted in for each one of these terms in my conservation equation the way that I will calculate that energy. Okay, let's start. I should know everything here except for the except for the displacement of the spring, and so I'm going to be solving for this delta x. And let's just go see if I don't have the information I need here. So it's an 8 kilogram cart, initially going at 5 meters per second. So the kinetic energy was 1/2 times 8 kilograms times 5 meters per second squared. I'm saying these out loud because before I plug these in, I want to make sure that they're in standard units, right? That they involve kilogram, meters, and seconds. Those are my standard units. Okay? The spring constant was given to me as 50 newtons per meter, and then I'm looking for the displacement. And so I know everything here except for that delta x. And so I get that delta x is 2 meters. Okay, let's do another one. So here we have a rock that's being shot straight up in the air. That means vertically up in the air with a slingshot that had been stretched by 0.3 meters. And we're going to assume there's no air resistance. Okay, so at the beginning, I'm going to put everything that I see here in my system. So that's the rock, it is the slingshot, and the earth. Okay? Slingshot is an elastic object. It's able, you can stretch, it's kind of like a rubber band, right? You can stretch it and it goes back to its original shape. And so it is possible to store elastic potential energy. At the beginning, I can see right here that they're implying that the rock is at the reference level for 0 gravitational potential energy. So I'm not going to include any EG. And it's not moving, right? It's not moving here. It's being held in place in the slingshot, but the slingshot is stretched. And so the type of energy that my system has is all stored as elastic potential energy at the beginning. Then at position B, it must be at the peak height, because the velocity is 0, so it's at the peak. It is much higher than it was originally, so that it has some gravitational potential energy. The slingshot is relaxed. Since the slingshot is relaxed, there's no more elastic potential energy. So all of the energy in the system is now stored as gravitational potential energy. So our conservation equation says that the change in the elastic potential energy equals the change in the gravitational potential energy. What they're asking me for is the peak height of the rock. Okay, I'm going to start with that conservation equation, and I replace each term with the way that I calculate that type of energy. Elastic potential energy, and I'm using the snapshot formulas, right? I want to know at position A, the elastic potential energy is 1/2 of the spring constant times the displacement squared. And then at position B, the gravitational energy is the mass times g times the height. Okay, so now I start plugging in, and I'm going to be solving for the peak height of the rock. So I'm going to solve for this h. Okay, so they gave me the spring constant of the slingshot. It's 100 newtons per meter. The displacement was and this is the displacement of the slingshot, was 0.3 meters. I'm going to square that. The mass of the slingshot, the mass of the rock is 500 grams. So this is something that I need to convert to standard units. 500 grams is half of a kilogram. G is 9.8, and then I'm going to be solving for h. So when I do this math, I get 0.918 meters. Let's look at 10. Here we've got a roller coaster, and it starts out at rest. I see that because it says velocity of 0 at the top of a mountain, and it's going to roll down this track, and then it will be moving at the bottom. Okay, so I'm going to put everything in here. I'm going to put the roller coaster, that's the cart, and the track, and the earth. Now, in this one, there is going to be some friction, and they're telling me that 10% of its energy is dissipated. That means 10% of the original energy. Okay, the original energy is all gravitational, because it says that the velocity is 0 up there at the top of the ramp. So I've got gravitational energy in this system to begin with. At the end, it's mostly kinetic, but 10% of the energy has been dissipated due to friction. And so my conservation equation is that the change in the gravitational energy equals the change in the kinetic energy plus the change in the dissipated energy. Okay, now I replace each term with the way that I would calculate that energy using the snapshot formula. Gravitational potential energy would be the mass of the roller coaster car times g times its height. Its kinetic energy would be 1/2 of its mass times the velocity at the bottom squared. Now, I'm not going to put the formula for calculating dissipated energy because they're telling me that 10% of the energy is dissipated. The original energy was the gravitational energy. And so I'm going to say plus 10% or 0.1 of mgh. 10% of that original gravitational potential energy is dissipated. I'm going to subtract that 10th of mgh from both sides. And so over here, I end up with 0.9 mgh equals the 1/2 mv squared. And they're asking me for the final velocity. Okay, so I'm looking for that v at the end. This is what I'm solving for. Okay, so I can plug in what I know, and as I plug in, I make sure that it's in standard units. The mass of the roller coaster car is 40 kilograms. G is 9.8. Its height there at the beginning was 5 meters. Mass again was 40, and I'm solving for V. So if I do that math, remember that we need to take the square root of that because in our equation we've got v squared. Then I get that the velocity is 9.391 meters per second at the bottom of that ramp.